Hello, I am Takeshi Yasui from Tokushima University. Today, I would like to present our recent research result. In this work, we demonstrated for the first time 100 Gbps class wireless transmission beyond the 420 GHz and present an ultra high-speed mobile backhaul technology towards the photonic 6G. This research was conducted as a collaborative effort between the Institute of Post-ALD Photonics, the Institute of Photonics and Human Health Frontier, and the Graduate School of Technology, Industrial and Social Science at the Tokushima University, and the Faculty of Engineering at the Gifu University. First, I will explain the research background. Towards the next generation mobile communications or 6G, the wireless implementation of mobile backhaul is becoming increasingly important. This figure illustrates the signal flow when transmitting information from a mobile device. For example, when sending an email, the signal is first transmitted as a radio wave from the device and received by a nearby base station. So here. The base station then forwards the signal via the optical link to the central office here. The central office identifies the base station closest to the receiver, and the signal is again transmitted via the optical communication. So here to here to here. Finally, so it is sent as a radio wave from the base station and received by a destination device. So in this way, the modern communication systems are realized through the integration of wireless and optical communications. However, in the conventional system, there has been a gap in data transmission speed between the wireless and optical links, preventing the full utilization of the ultra-high-speed capability of optical communications. In 6G, this gap is expected to be eliminated, enabling the much higher overall communication performance. Here, the mobile backhaul refers to the communication link that connects the central office and the base station. So here. The coverage area of base station is called the cell, which is typically on the order of several kilometers in 5G systems. In contrast, in 6G, the use of higher carrier frequency enables ultra-high speed and large capacity communications, but also result in a higher propagation loss. As a result, the cell radius is expected to shrink to around 100 meters. Consequently, a much large number of base stations will be required to cover the same area. In addition, the introduction of mobile base stations such as the drone and the hubs make it increasingly difficult to connect all base stations using optical fiber. For this reason, the wireless implementation of the mobile backhaul has become a key challenge. In particular, while the 300 GHz band for 6G is expected to be a congested higher frequency bands such as 350 to 600 GHz are attracting significant attentions. Although these bands suffer from higher atmospheric attenuation, they offer a much wider available bandwidth, making them promising for the high capacity in mobile backhaul communications. As a key technology realizes this, we employ an optical frequency comb. This slide shows a technological evolution of the optical frequency comb. From the first to the second and then to the third generation, the system size has been significantly reduced. Third generation is known as a microcavity microresonator comb or microcomb. It is generated by a coupling a CW laser into a microresonator based on the optical waveguide, producing a comb-like spectrum here, consisting of equally spaced optical frequency mode. Such an optical waveguide-based device can be mass-produced using a semiconductor fabrication process, enabling a compact size, low cost, and high reproducibility. In addition, so they are highly compatible with silicon electronics and silicon photonics. Therefore, they are attracting attention as a practical solution to overcome the limitation of the conventional optical frequency cone, which, despite their high performance, have the lacked the practicalities. More importantly, because a microresonator is extremely small, the spacing between the optical frequency mode, namely the repetition frequency or FREP, become very large. In this case, this frequency reaches the order of several hundred gigahertz, making it possible to match the carrier frequencies used in 6G. By leveraging the characteristics, the terahertz wave generation become possible. This slide illustrates the underlining the principle. First, the two adjacent modes are extracted from the microcomb from the spectrum of the microcomb using optical bandpass filter. Since these modes are optically waves, so their superposition in the time domain produce optical beating, namely the optical bit signal. The frequency of this bit signal is exactly equal to the frequency difference between two modes, that is the FREP. By converting this optical bit signal into the terahertz domain via the optical to terahertz conversion or photomixing, the corresponding frequency component can be irradiated in free space, resulting in a terahertz wave. A key advantage of this approach is ability to generate the ultra-high frequency terahertz wave with a low phase noise. Furthermore, it enables the simultaneous achievement of ultra-high frequency operation and low power consumption, which is difficult to realize with a conventional electronic approach. As shown here, microcomb are highly promising technology. However, in conventional system, although the microresonator itself is compact, a large number of optical components are required around it, resulting in a bulky and complex overall setup. To address this issue, we developed the fiber-coupled microcomb by directly connecting the optical fiber to the microresonator chip. This approach enables a significant miniaturization as well as a high reproducibility and improved performance. With this fiber-coupled microcomb, we achieved not only a substantial reduction in the system size, but also long-time stable operation for over 2 weeks. In addition, the stable operation was maintained even under the environmental temperature variation exceeds 50 degrees. This is our terahertz communications experimental setup, which is based on the microcomb generated from a fiber-coupled microresonator. While I will skip the detailed explanation, this system consists of 5 key technologies. First, the microcomb itself. Second, the low noise optical amplification to achieve the high output power. Third, the high order modulation of the optical signal. Fourth, the terahertz wave generation using modulated optical bit signal, namely photomixing. And finally, so the high sensitivity detection of the generated terahertz signal. This slide shows a representative example of the measured result. In this experiment, we employ the 60 CAM modulations. The top left figure shows the ideal constellation, which consists of 16 symbols arranged in a 4x4 grid, which each point represents a data symbol. Ideally, each symbol should be located at a fixed position. However, in practice, they fluctuated over time due to the noise and other impairment. The superposition of these fluctuations forms a constellation diagram, like here. Here we show the constellation diagram at the data rate of 20, 40, 60, 100, and 120, 12 gigabps. As the data rate increases, the spread of the constellation point become larger, indicates a degradation in the signal quality. From these constellations, we calculate the error vector magnitude, or EVM, which is a quantitative metric of signal quality. The right-hand graph plots the EVM as a function of data rate. Although the EVM increased with the data rate, it remained within the acceptable range even at the 112 gigabps. This confirms that the wireless transmission up to the 112 gigabps is achievable. This slide shows the global positioning of our result. The plot on the left compares the data transmission rate, where the horizontal axis represents the carrier frequency and the vertical axis represents the data rate. Up to around 400 gigahertz, many studies have been reported, including the demonstration exceeding the 100 gigabps. However, the frequency region about 120 gigahertz has remained unexplored for the transmission speed beyond 100 gigabps. In this work, we demonstrated for the first time wireless transmission exceeding the 100 gigabps in this frequency range. The panel on the right illustrates the impact of 100 gigabps transmission. For example, the 100 gigabyte 4K movie can be downloaded in approximately 8 seconds. Additionally, around 4,000 simultaneous streams of 4K video at the 25 megabps can be supported. Furthermore, 1 terabyte of data can be transferred in about 80 seconds. This result indicated that the near instantaneous ultra-high-speed communications can be achieved. Finally, so let me summarize our work. In this study, we demonstrated the wireless transmission exceeding 100 gigabps in the terahertz region above the 420 gigahertz, making a new milestone in terahertz communications. We believe this result will represent an important step towards a microcomb-driven terahertz communications, namely photonic 6G. This concludes my presentation. Thank you for your attention.